Alright, welcome back everybody. In this video we're going to start looking at examples from the Chain Rule Part 2 lesson. And the first batch of examples are ones where we're going to apply the chain rule multiple times because we have more than two functions in composition. In order to do this, we just want to identify which is the outermost function to start with and apply the chain rule from there. And we'll end up having to apply the chain rule multiple times along the way in the process to find these derivatives. So let's look at example 1. We're going to find the derivative if y equals cosine squared of the quantity 7x plus 2. Now in order to do this, it's a good idea to think about this function as the cosine of the quantity 7x plus 2, that whole quantity squared. Anytime we see a trig function with the exponent up here, like a cosine squared or a sine cubed or anything like that, it's good for us to think about the function that way before we start trying to take the derivative. So now when we look at this, we recognize that the outermost function is raising something to the second power. So I'm going to take the derivative of the outside, leaving the inside the same. That drops it down to the first power times the derivative of the inside. And now the derivative of the cosine of the quantity 7x plus 2 is another situation where we're going to need to apply the chain rule. So we still have 2 cosine of 7x plus 2 in the front here. And then the derivative of cosine of 7x plus 2, the derivative of cosine is negative sine, so I take the derivative of the outside, leaving the inside the same, times the derivative of the inside, the derivative of 7x plus 2. And I'm not going to go ahead and write another line here since the derivative of 7x plus 2 is pretty easy to find. I'm just going to write that in, and that's 7. And then the last thing I want to do is clean up my answer, get all my constants out to the front, and write it in a way that it is not ambiguous from a notational standpoint. And I end up with my derivative of this function being negative 14 cosine of the quantity 7x plus 2 sine of the quantity 7x plus 2. Alright. Example 2. Find dy dx if y equals sine of the quantity 3x squared plus 2x to the third power. Notice the difference between this and example 1. In example 1, the cosine function was being raised to the second power, whereas here in example 2, only what's inside the parentheses is being raised to the third power. And that means that my outermost function in this example is the sine function. And so when I go to find the derivative, I take the derivative of the outside, leaving the inside the same, times the derivative of the inside. And what's inside the sine function is the quantity 3x squared plus 2x raised to the third power. And now I'm going to take the derivative of that. So I still have my cosine of 3x squared plus 2x raised to the third power. And then my derivative of the outside of that is going to be 3 times the quantity 3x squared plus 2x raised to the second times the derivative of the inside, the derivative of 3x squared plus 2x. And so I'll take the derivative of that. And the derivative of that is going to be 6x plus 2. And now I'm just going to clean this up. I'm going to have a 6 in front because I'm going to factor 2 out of the quantity 6x plus 2. So I've got 6 times the quantity 3x plus 1 times the quantity 3x squared plus 2x to the second cosine of the quantity 3x squared plus 2x quantity cubed. And there's my derivative in example 2. Oh my goodness, look at example 3. Whoo! We have what? 1, 2, 3, 4, 5 functions in composition here. This one's going to be a doozy. So I look, and my outermost function to start with is raising something to the 4th power. So dy dx is going to be 4 times the quantity tangent of secant of x squared plus 5 to the second plus 3 quantity cubed times the derivative of tangent of secant of the quantity x squared plus 5 quantity squared plus 3. Okay, and now I need to take the derivative of what's in there. I have a feeling this is going to get a little bit unwieldy with so many functions in composition. And now when I take the derivative of this, tangent is the outermost function here. So I'm going to take the derivative of the outside, leaving the inside the same. That's all secant of x squared plus 5 quantity squared plus 3. And then I need to multiply that times the derivative of the inside, the derivative of secant of x squared plus 5, the quantity squared, plus 3. Alright, charging forward. I have all this stuff that I just need to recopy here. Am I missing a parenthesis there? Yeah, I am. Right here. Right here. I have the parentheses. Wait a second. Alright, I see what I did here. I put an extra parenthesis in way back here. Shouldn't have had that 3 inside of the tangent function. So I need to go back and fix what I did here. Because that 3 is not inside the tangent function. And so in this second line, I'm taking the derivative of the tangent function plus 3. Well, the derivative of the tangent function gives me exactly what I've got here. And then the 3, the derivative of that is 0, so I don't need that in my function. And then that's going to be multiplied by the derivative of the inside, which is secant of x squared plus 5 quantity squared. Alright, we've got all that worked out now. Okay. This is a crazy problem. So many things to consider. Alright, now the derivative of secant of the quantity x squared plus 5 quantity squared. The derivative of secant is secant tangent. So it's going to be secant of x squared plus 5 quantity squared tangent of x squared plus 5 quantity squared times the derivative of the inside. And we're almost done. We're almost home free. We've got 4 tangent of secant of x squared plus 5, the quantity squared, plus 3 all to the third, times secant squared of secant of x squared plus 5 quantity squared times secant of x squared plus 5 quantity squared tangent of x squared plus 5 quantity squared. And now we need to take the derivative of the quantity x squared plus 5 to the second, derivative of the outside, leaving the inside the same, times the derivative of the inside, which is just 2x. So I'm going to take care of that right there. Alright, now I want to clean this mess up. So I've got dy dx equals, I'm going to bring my constants and such forward. So I've got 16x. That takes care of the 4, 2 here, and the 2x here. Then I've got the quantity x squared plus 5. I've got secant of the quantity x squared plus 5 quantity squared, tangent of the quantity x squared plus 5 quantity squared. That takes care of this x squared plus 5 and these two factors. And then I've got a secant squared of the secant of x squared plus 5 quantity squared. That takes care of this factor. And then all I have left is the tangent of the secant of x squared plus 5 quantity squared plus 3, that whole quantity to the third power. And there's my derivative. We best hope we don't run into functions where we've got 5 nested functions in composition, because taking the derivative of it gets a little bit hairy sometimes. Alright, that's the end of this video on the first 3 examples from our Chain Rule Part 2 lesson. We're going to handle example 4 in the next video. See you next time. Have a great rest of your day.